Hi, this is a short video looking at tutorial 8, question 1e. So what we hear is we've got a vector line integral around a triangle, as mentioned in the picture here. And it's going around clockwise. So the first thing I would do for any vector line integral, check if the curve is closed, and it is. When it is closed, then what we can appeal is to one of the big great theorems called Green's theorem. So Green's theorem is definitely the way to go. So this is essentially an example of Green's theorem, if I spell it properly. So what Green's theorem states is if you're transversing a curve anti-clockwise, then the vector line integral can be equal to summing over the enclosed of Qx minus Py integrating over the whole area. Then Qx minus Py is sort of the either measures how non-conservative the function is, and if we're adding up the non-conservative parts, or it can also be thought of as the rotation. So this is summing up the rotational aspect of all the bits in the middle to give you the total rotation just on the boundary. Now, but it does need to be anti-clockwise for it to work properly. And we've got a clockwise curve. So what happens since it's going the opposite direction? How does it impact it? Well, it's just going to change it to be a minus sign since we go opposite direction. So we got the clockwise, so it's going to be negative. That's the clockwise part of this double integral. So that's what it appeals in this case. So P here is just the first term, Q is the second one. So Qx, so Py, might be easy to write down first. Part of this first term will give you x. Qx is the part of this thing which will give you 1. So plugging what we've got in here, Qx is 1, Py is x. And then we integrate to A. And we integrate this region. Now, it's easier to split it up as a type 2 region. So integrating, cutting in this direction first. So therefore, we really want to bound the whole thing by functions of x. So if you want to integrate x first and then y second. The limits for y, well, y goes from 0 to 1, so it's the outside limit, so that's easy. The inside ones, we need to know the values of these functions here. So this here is x plus y equals 1. This one here is y minus x equals 1, sort of by symmetry. And we can make x the subject, so we can say that x is equal to 1 minus y, and this bottom curve then is x is equal to y minus 1. So that will become our boundary curve. So the bottom curve is y minus 1, top curve is 1 minus y. It's got odd symmetry, which we could exploit if you wanted to. So then it's a double integral you do directly. As I said, because of this sort of odd symmetry here, the integral of so because it's symmetrical, one here is an even function. So it'd be twice the integral from 0 to 1 minus y of 1. And x here is an odd function, so integral the limits of plus from minus a to a of an odd function is just going to give you 0. So we could actually, using symmetry, reduce it down this if we felt like it. And again, you could do some tricks. That's minus 2, 0 to 1 of 0 to 1 minus y. Dx dy. And you can see that really just corresponds to minus 2 times by the corresponding area. And what it's an area of is this triangle here. And the area of that triangle there is length 1, height 1. So it's going to be equal to minus 2 times by 1 times by 1 times by 1 times by half, I should say. So, which gives you the answer of minus 1. So that's the alternative way. Maybe I'll just, lets me also do it properly. So ignoring all the tricks of symmetry and area and all those sort of things too. You can just treat it like a normal simple double integral. And that is integrate the inside one first. So x minus x squared on 2. Subbing in y minus 1 and 1 minus y. And subbing those in, if you sub 1 minus y and 1 minus 1, you end up getting two minus y on the top. Subbing both of them into the squared, they end up cancelling out, which is the observation I made earlier, effectively. Dy. And then integrating this term here, you get 2y minus y squared from 0 to 1. Sum the 1s, you're getting 2 minus 1. Sum the 0s, you get nothing. And you're getting minus 1 as the answer as before. And which wasn't that hard, so you didn't really have to use those tricks to get the answer fairly quickly. But big picture is that a Green's theorem allows you to convert a vector line integral into a double integral, often with an integram, which is a bit easier to deal with. And therefore, it's a really useful trick when you've got closed curves. So always be on the lookout for that. So that's really the big moral of the story. And otherwise, when you get a double integral, proceed like you've done earlier in the course. So I hope that helps.